I'll discuss a new Datacom laser source standard that is being worked on. All of the information I'm going to discuss with you is on the website for the MSA, including a lot of great technical articles. So I encourage anyone that's interested to jot this down and go there directly. Why a new wavelength grid standard for Datacom? So we're all familiar with the orthogonal axes to increase optical data rate. Baud rate, which is speed, more spatial channels, parallel, WDM, wavelengths, or higher order modulation. And then coherent adds the TETM, but these are the major ones. So up until 10 gig, the Datacom stuff was all single wavelength NRZ. 40 and 100 G for the mainstream, we transitioned to 4 wavelengths NRZ, and 200 and 400, we transitioned to PAM4. 800 gig is just starting in the IEEE. Initially, that may be 8 wavelengths, but in volume, we expect that to be 4 wavelengths as well. And I think there'll be a robust modulation debate, trading off baud rate, maybe with a higher order. However, there is a broader industry debate, and that debate really started when PAM4 was first adopted, which is between more channels versus higher order modulation. And more channels is either WDM or parallel, and higher order modulation goes hand in hand with DSP. This isn't a place for this debate, but that's the basis for the standard, which is that a lot of work going into DSP. The IEEE, by and large, is sticking with 4 wavelengths going to higher order modulation. But what this MSA is providing is higher WDM count alternatives for emerging applications. Here's just a few administrative items. The website repeated. The MSA was formed in April of this year. I'm the chair. Matt Sisek of AR Labs is the editor, and David Lewis is the associate editor. I'll touch on status towards the end. And then Christine Rauer is marketing. The objective for the first standard is to specify 8, 16, and 32 wavelength CW sources. There is no link specification, so no modulation. It's really left for the applications to develop. And the specs are optimized for photonic integration, both photonic integration in generating the laser sources and photonic integration for how the multiple wavelengths are used. Next, let me go into the wavelength grids and some of the thinking behind where we are today. Oh, one more organizational. We have 11 promoter members. I'll show you who they are. These are standard members. They signed an MSA document with legal obligations like NDAs. These are the members that are developing the specifications, licensing IP, voting on the standard, and actively will promote the MSA. We tried something new, which is we created an observer category. This is a category that has no legal or other obligations. There's no document to sign. So the observer members, they don't get to vote. They don't get access to the NDA material, but we do keep them informed on an ongoing basis so that at some period after the MSA discusses that, we make information available. And then they also get to comment and review through promoter members. And that seems to be working reasonably well. Here are the promoter members. There's 11 of them. Again, I'm not going to go through this. This is on the website. You're welcome to peruse, including contacts from all these companies. And here are the observer members. Again, a lot of interest, but it was easier for all of these folks not to have to deal with NDAs and agreements. Okay, let's move into something substantive. So let's review the high volume grids that the industry has used. I'm showing here a subset of O-band. I'm only going out to 1340. O-band goes somewhat further to longer wavelengths. And this is drawn so it spans the first WDM high volume Datacom grid. There was an LX4 grid which preceded that, which has a larger span, but that really didn't hit high volume. So the first high volume WDM grid was adopted based on the 4 shortest CW-WDM wavelengths specified by ITUT, and it was applied to 40 gig LR4. And I'm showing the nominal wavelength range, or the full wavelength range, as in the IEEE spec. By the way, that grid is used, also referred to as CW-WDM4 because it's used for the predominant 100G standard, FR4 200G, FR4 400. It's likely going to be used for 800G as well. Second grid that was adopted was for 100G LR4. This is based on the ITUT DWDM specification and is colloquially referred to as LWDM. And you can see the 4 wavelengths here clustered around 1300. And one of the reasons, although not the only one for this, was the low dispersion. And then we came along in another IEEE project and extended the LWDM wavelengths to shorter wavelengths to get 8 of them. One other thing I'd like to, Paul spoke about challenges of testing. One of the big challenges in testing these optics, especially as we're going to higher order modulation, is there's no effective amplification in O-band that covers, for example, the CW-WDM range or even the LR8 range. If you look at an example PDFA gain 3 dB bandwidth, you can see that spans from a little bit below 1290 to a little bit over 1310. It's a gradual roll off, so you can use it somewhat beyond that. But that's a real limitation if you want to have amplification, starting with testing. But furthermore, if you ever get into highly lossy situations, you don't have anything outside of this region. So let's look at the first grid that the MSA is considering. There will be 3 spans. 36 nanometer span is the widest. I'm going to start out with the first the grid. I'm only showing center wavelengths here because it's actually complicated how they're used. But this is an 800 gigahertz grid based on the DWDM specification from the ITUT. So you can see we're actually picking up 6 out of the existing LWDM wavelengths, and we're right smack in the middle of the CW-WDM grid. So this is a very comfortable area for laser manufacture, very comfortable area for people that have been working on photonics for high volume. And we also see that it very nicely fits in the PDFA gain. There's other advantages to this kind of a grid, which has to do with photonic integration. One other feature of this grid is you notice this is 1+8. So there's actually 9 wavelengths specified. So what you have here is 8 data carrying wavelengths and then an auxiliary wavelength that if you want to have a synchronizing or clock signal or something like that you want to distribute, that's available in a specified fashion. Or you could just use it for carrying more data. But it's anticipated that the data carrying wavelengths will be the nominal 8. Then to go to 16+1 wavelengths, we just fill in, we go from an 800 gigahertz grid to a 400 gigahertz grid, and we have 16 wavelengths. And then to go to 32 wavelengths, we fill that in again to a 200 gigahertz grid. And this is a roadmap where you can see that initial products could start with 8 wavelengths. The design could anticipate 16 wavelengths, both for the suppliers and for the transceiver manufacturers, and eventually go to 32 if in fact the technology supports it. So this is another feature of the MSA. It doesn't per se provide a single solution. It's more like a smorgasbord of solutions so that different applications can be tried. Here is the 18 nanometer span. So what we can see is that for 8 wavelengths, we start out with 400 gigahertz spacing. This is a subset of the earlier one. So this is actually 8 out of the 16 wavelengths from the 36 nanometer grid. And then in the same fashion, we go to 200 gigahertz to get 16 wavelengths, and we go to 100 gigahertz to get 32. At 100 gigahertz, we really are starting to get into DWDM territory. So lots of important issues like 4-wave mixing come in. And again, I encourage you to look on the website. We have some very nice technical work done looking at the issues associated with grids like that. So again, you can see this is all in very familiar territory for people building equipment and lasers. 4 of these wavelengths overlap. And furthermore, from a testing or actually a distribution, signal distribution standpoint, we fit very nicely in the PDFA band. And then the third grid is 9 nanometers. It only has 8 and 16 wavelengths as we're choosing to stop at 100 gigahertz grid. There's a number of parameters that are obviously driven by the finest spacing. And so 50 gigahertz is deferred to the future, but obviously it can be expanded. But let's learn first before we jump into more aggressive grids. Let me share with you a couple of more specs. One is there will be 3 power classes. Type 1 is basically the eye safety limit, which means that if you integrate the total power across all the wavelengths, whether it's 8, 16, or 32, it won't exceed the eye safety limit of the shortest wavelength. So that's why you can see that when you go from a narrower grid to a grid which contains shorter wavelengths, the eye safety limit actually drops. And then there's 2 additional types. One is a eye safety limit minus 6 dB. So this is, for example, where you have excess link margin in whatever your application, and you really want to lower power. And then the second type is eye safety limit plus 6 dB. So this requires additional safety measures. So let's say the laser source would have to be on the card, for example, so that the fiber is not exposed to the user, whereas the other types could have the laser source remote. And AOP is average optical power. The other interesting menu choice is for the type of grid spacing. So type 1 is where the drift allowed is actually greater than the grid spacing. So you can see the proposed center wave variation here is plus or minus 5 nanometers with additional 5 nanometer drift allowed during operation due to environmental conditions. And then the type 2 is sort of the more traditional where you're holding things within the band in terms of tracking. And again, this is geared toward very specific photonic integration technologies. Let's just talk about where we are from a status. We just published our first public draft. It is on the MSA website. I'm giving you the direct link here, but you can also just go to the site and click on the in the technical documents. This is out from promoter and observer review, and we'll be starting comment resolution. We've already done several cycles of this. So this is a result of refinement and addition. And through the ECOC, we're inviting the entire community to, if you have interest, to look at it and provide comments. Contact the editors, myself, or any of the promoter members, and we very much welcome comments. There's multiple technical issues that are still open, so we still have a lot of work to do. We'd like to publish no later, but then by OFC 2021, which is now moved to June. We may get it out sooner, but I hope it's no later than that. And that brings us to our thank you slide. And I did leave room for questions. I think we've got a little bit of time. Is that right, Glenn?
Hey, we've got 1 minute, Chris.
1 minute. Oh my God.
Yes.
I think we must have started late because I've got 16 and a half minutes that I've used.
That you used up, yes. But you're helping the overall team effort here. You're catching us back up.
You and Horizon below me big time then.
Hey, we didn't have a bunch of questions come in, but I do have one for you. I mean, did you folks consider C-band instead of going back and trying to shove everything into O-band? I mean, that's
a great question, and there are people that are betting on C-band for Datacom. There are people that have done that bet before and lost. I think it's a little bit less clear now, so we'll see how the market plays out. There's certainly arguments for that, which is there's a lot of technology developed. However,
amplification is easy, right? I mean, we've solved all those problems. Amplification, as you mentioned, the PDFA
amplification is probably the biggest one. However, on balance, when we really carefully looked at where all the experiences in photonic integration, in developing lasers and very high volume sources, it's all in O-band, and it's all going to continue in O-band. So we're really leveraging a huge industry infrastructure, and our bet is on O-band, again, because that's where all the Datacom experience is. But there are several guys that are betting that high wavelength count Datacom is going to be in C-band. And that's the beauty of the free market, that, it doesn't matter what you think, it's the best products that are going to win. So we'll see how that plays out. But the guys that have made that bet before, I used to tease them mercilessly, and they did go down in flames. So occasionally over beer, I get to tell them I told you so.
Fair enough. Fair enough. And I would imagine, and then you do open yourself up to a host of other chromatic dispersion and other concerns that you don't have to care for.
Right. So that again is kind of the biggie, that you really do need the DSP. And the whole premise here is that it allows you to do things very simply. By increasing the parallel channel, you could return to NRZ, or you could stick with PAM4 when others have to go to higher order modulation or coherent. And again, that's another huge debate that we don't have time here. I certainly encourage people to attend the rump session at OFC 2021. This is a shameless plug. Ilya Lubomirsky and I will have a WDM team versus a DSP team duke it out. So we're structuring it as a fight to the death. And the few that leave the bloody field of battle will carry the WDM or DSP flag triumphant. But we encourage everyone to watch the rump session for that debate.
Looking forward to it. Looking forward to it. Thank you again, Chris. I appreciate it.
All right, Glenn. Thank you for the kind invitation.